Okay, so today we'll do trigonometric ratios and standard position. So recall that sine theta is equal to opposite over hypotenuse. The cos theta is equal to adjacent over hypotenuse. And tan theta is equal to opposite over adjacent. And with those, we have our reciprocal functions, which is cosecant theta is equal to hypotenuse over opposite. Secant theta is equal to hypotenuse over adjacent. And cotangent theta is equal to adjacent over hypotenuse. Now you'll see, of course, the primary trig ratios more often rather than the secondary ones, but it's good to know both of them, and by all means, there could be questions using the secondary ones too. So going back to this idea of a standard position for angle, it's on the Cartesian plane, and we have a ray extending outwards. An angle formed here, let's call it theta, is formed between this ray, which is called the terminal arm, and the positive x-axis, or the initial arm. So when we can be given a point anywhere in the Cartesian plane, and there will be a ray that extends towards it and will form an angle theta. So in this case, let's say we have a point here that's 5, 4. So over 5 up 4. So we can sort of determine the trig ratio of theta using knowing this point. So as I just said, this means that it's over 5 and up 4. So therefore, we know that this length is 5 units, and this length is 4 units. And to calculate the hypotenuse length, we can just use Pythagorean theorem. So let's say hypotenuse is equal to the root of 5 squared plus 4 squared. Hypotenuse is equal to root of 41. So that's length there. So since we know all the side lengths of this triangle, remember the trig ratios are just ratios of the lengths, so we can calculate all the trig ratios for this triangle. So let's say, take sine for example. Sine theta would be opposite over hypotenuse. So sine theta will equal 4 over root of 41. From there, we can also find all the others from the side lengths, but I'll just keep it at sine theta for now. And this is a rather simple scenario. So I want to take you guys back to this idea of reference angles. Okay. Say we have a ray extending this way. This is the angle theta. Let's call this the reference angle alpha. Now what's interesting about a reference angle is that the trig function theta, so let's say cos theta, will somewhat equal the trig function relating to the reference angle, so cos alpha. So the value will be the same, except the sign might change, and that depends on the quadrant that the angle is in. So let's remember quadrants. We typically look at it as quadrant 1, 2, 3, 4. And now starting from the bottom left quadrant, we can assign the word or the letters for cast going counterclockwise. So C, A, S, T, cast. So the letters correlate with which trig ratios are positive in that quadrant. So in quadrant A, all trig ratios are positive. And in S, everything is negative except sine. So sine is positive and everything else is negative. And as you can guess, in T, tan theta is positive, and everything else is negative. In C, cos theta is positive, while everything else is negative. So in this case, we were looking at sine. Sine of theta would in fact equal to sine of alpha. Since theta is in a quadrant, the ray is in a quadrant, where sine is positive, these angles will be equal. But if we look at cos instead, so we look at cos theta, cos of alpha will give a positive result, right? It's an acute angle. It'd be like in the A quadrant. This will give a positive result. But theta won't be positive because in this quadrant, cos is negative. So cos of theta would equal negative cos alpha. And that's how the sign of the function is related to the quadrant that the angle ends in. And so we can use this relationship with the quadrants and with the reference angle to solve for the value of trig ratios of different angles. Now, another thing that we can now talk about is determining an angle from a ratio. So if we're given, say, sine theta, and asked to find the possible values of theta, where theta is between 0 and 360 degrees, we can use the standard position of angle to help us solve it. So, let's say sine theta is equal to 1/2. Well, what does this 1/2 tell us? It tells us that hypotenuse is 2, and that the opposite leg is 1. And we also know that this is positive. So in which quadrants is sine positive? It's positive here, and it's positive in 2 of these quadrants. So therefore, we know that this answer can't be in these quadrants. We can't have angles that go there, since if it was there, it'd be negative, but it's not, it's positive. So let's try in these 2 quadrants. So here, hypotenuse is 2, opposite is 1. And we can also draw on the other side too. The hypotenuse is 2, opposite is 1. Now here, this leg would be root 3. You can solve that by doing Pythagorean theorem. It's also a special triangle, if you know that. Here, this is negative root 3. Now, this doesn't matter, since sine only looks like the 1 and the 2. And in these 2 quadrants, they are the same. So now, from here, we want to determine the angle. If we want to determine the angle, what we can do is look at the special triangle ratios. So this is a special triangle, which we'll talk about later. But well, that's an ugly triangle, but oh well. In this triangle, this angle here is equal to 30 degrees. This angle here is equal to 60 degrees. And this angle is, of course, right. So from that, you can know that this is 30 degrees. And you can also know that this is 150 degrees. So those will kind of be your 2 solutions. But say you don't know special angles, then you can't really do much without using a calculator, using an inverse sine function, which would sort of make this whole thing pointless. But what you can do from here is to determine the other trig ratios. Since we've now figured out all the sides, we also know that cos theta can be root 3 over 2 or negative root 3 over 2. You know that tan theta could be 1 over root 3 or negative 1 over root 3. So we've been able to determine some various other solutions. But sometimes the question could also say that find the solutions in quadrat 1. So it would be draw that in better place. In quadrant 1, say if the question asks that we only find solutions there, then you can not mention all these negative solutions, since all the solutions here are positive. Now we can talk about angles that have identical trig ratios. So some angles with identical trig ratios are coterminal angles, and that makes sense because they end on the same arm. So let's say we have an angle here. If this is 30 degrees, then going all the way around like this, which would get us, 390 degrees. The trig ratios, so I'm just going to use sine generically, of 30 degrees will equal to the trig ratio of sine at 390 degrees. Note how it's related by a full rotation. So all of these angles that have the same full rotation will have the same trig ratio for sure. And that sort of refers to references the cyclic nature of the trig functions. So if you know, sine functions look like something like this. See, every so often, every given period, values will repeat, and that's sort of represented by this full 360-degree rotation. There's also another scenario, and that's just if the reference angles match and the sine matches, and this really depends on the specific trig ratio. So if we look at here, say we have another ray going out, this is 60 degrees. Another angle that can match this is over here. When the reference angle is 60 degrees, this entire angle would be 120 degrees. So, since these are both in a quadrant where sine is positive, because remember, cast, this is A and S, sine of 60 degrees would equal the sine of 120 degrees. Even though they're not a full rotation apart, they are equivalent. And that can again be seen in the sort of trig functions, where this point here matches this point here, even though they're not a full rotation apart. But this sort of relationship really depends on your specific trig ratio, since their signs change depending on the quadrant. So make sure to sort of read the question carefully and to write in cast if you need to, just help you get everything sorted, get everything in place. And one final thing is, due to the cyclic nature of sine functions, it goes on and on and on. There are actually an infinite set of solutions for any sort of sine ratio. So if I say that sine of theta is equal to 1/2 again, but I don't restrict the domain of theta, so theta can be anything, there are an infinite number of solutions. So questions will generally pretty much always restrict it, but there is a way to express it, express these infinite solutions, but sort of beyond what we're going at right here.